Hi students, so today we start Fortran lecture 12 and today I'm going to talk about one more Simpson's rule for numerical integration. This is the 3/8 rule. I'm Dr. Ganguly. Now you know that as far as definite integrals are concerned, for example of the form a to b fx dx, you can calculate these actually by figuring out this region which I have shaded here. So if we take this function f of x, we have the bounds x is a to x is b, then the integral is going to be given by the cross section which is shaded here. So essentially all the numerical integration methods, they try to come up with this shaded region and therefore they try to estimate the integral. So in the previous lecture, I discussed about the Simpson's 1/3 rule, and this rule is given as follows. Now here what happens is that you have h by 3. That is why it is called the 1/3 rule. So it is 1/3 h, and then you have this particular series. You have fx0, 4fx1, 2fx2, 4fx3, and so on. And if you calculate this particular sum, then you are going to get this integral here after you multiply it by h by 3. Now, how does this method work? If we look at the function here f of x, then what we do is that we partition this domain between x is a and x is b into a number of segments. Each of these segments has the same length which is given by h. And then what we do is that we are going to assume a quadratic variation here. So if we assume a quadratic variation, then essentially we get this particular formula. Remember in the trapezoidal rule, we took a linear variation here. So essentially there were all these trapezoids out there. Now what happens in the Simpson's 3/8 rule is that we consider this region to be cubic. And in doing so, we get a slightly more complicated formula which I have given here. And an interesting thing about this formula is that you get the 3 by 8 into h term, and then you get this series here. You get fx0, you get some of the terms involving 3, and you get some of the terms which involve 2 here as the coefficient. So essentially if we are able to calculate this sum, then we can estimate the integral given here. So that is how you use the Simpson's 3 by 8 rule. So what I have now done here is that I have written the same expression out here, and then I have taken the terms which have the coefficient of 3, the coefficient of 2, and I have separated them out using different colors. So of course we have the terms fx0 and fx1, or rather fxn. These have coefficient of 1. Then we have all these terms involving fx1, fx2, fx4, fx5 to fxn minus 1. These have the coefficient 3. And then we have the terms fx3, fx6, fx9 all the way to fxn minus 3, which have the coefficient 2. Now, one of the things you will see is that this particular Simpson's rule, this requires n to be 3, 6, 9, 12, and so on. And you can actually see that this is required so that this summation can be obtained. Now, if we try to write this sum out in terms of a summation, we will get this expression here. So of course the first expression simply becomes fx0 plus fxn, but then you have 3 and then you have fxk. K goes all the way from 1 to n minus 1, but you exclude all the multiples of 3. So this is particularly important that any multiples of 3 are excluded. You can see here that you have fx1, fx2, but fx3 is missing here, fx6 is missing here, and so on. And the multiples of 3 are present in the terms involving the coefficient 2. So you can see that here in the second summation, you essentially go from k is 1 to n by 3 minus 1 fx 3k. You also see here that you have the n by 3 term here. Therefore, n has to be a multiple of 3 for this whole summation to work out. Now, before we proceed further, we will try to simplify the logic here or the math to bring it to a simple form and look at some standard formulas which are out there. So what we do is I rewrite the expression here for I, which we found out in the previous slide. Remember, throughout n is a multiple of 3, h is b minus a by n. Now we know that x0 is a, x1 is a plus h, x2 is a plus 2h, so xk is going to be a plus kh. That's the general term. Now from this general term I can also write that x3k would be a plus 3kh. So I simply substitute 3k here, so I get that term here. Now once I have xk, I have x3k, I can put it in this equation, and also I know x0 is going to be a and I know xn is going to be b. So that's going to help me express this in the form a, b, h and so on. So I take this expression now and I make all those substitutions, and so I get this equation here, which is something which is more easy to figure out. Now we know that a is the starting point of the integral, b is the end point, and then as we proceed further forward to the right hand side we get a plus kh terms, and here we have a plus 3kh terms. Let us now look at a very popular special case which involves n equals to 3. That gives a nice simple formula. So if we consider n is 3, then I can take the expression for I and I can substitute n is 3 here. So I will get 2 here. So essentially, as far as this summation is concerned, it goes from k is 1 to 2. Of course, excludes any multiple for 3, but in this case the multiple of 3 will simply not come because k is going to be 1, k is going to be 2, there is no k is 3. Now as far as the second summation is concerned, n by 3 will be 1 and 1 minus 1 will be 0. So this is simply going to go out of the case where n is 3. So there is going to be no term coming from this term involving coefficient 2. So essentially I can write this I out in this manner. So I have FA, I have FB, and then I have two terms here. The first involves k is 1 and the second involves k is 2. So this is the simple expression I get for the case n is 3. Of course, remember that h is going to be b minus a by n and n is 3 here. Now we are going to subject this rule to a numerical example. We have solved this problem in Math Tutorial 6. I'm going to leave a link to that video in the end screen. And you can see here that as far as this integral is concerned, it can be expressed as 1 by 3, 3 log 2 minus log 5, which I can write as 0.1566678676. Now, of course, if you want to do this particular integral, you can substitute 1 plus sine x equal to t, and then you can simplify and get this closed form solution. Now, in many cases, closed form solutions are important because they help you check methods. If you can get it, of course, it's very fast. But many integrals are out there which are not amenable to closed form solution. In those cases, you need numerical solutions like the one I'm going to discuss today. So let us now proceed forward with n is 3. Of course, we know a is 0. That's the lower limit of the integral. And b is pi by 2. That is the limit here. So I can write the expression I like this, which we derived before. And then we put a is 0. We put b is 2 pi. A plus h is simply going to become pi by 6 and a plus 2h is going to become pi by 3. Remember, h is pi by 6. So you have to do some additions here to get these particular values. Now, of course, once I have this expression, what I need to do is calculate all these values at the different points for this given function. So let's do that. We take the function here. Function is cos x divided by 4 plus sine x into 1 plus sine x. The first thing I do is I substitute x is 0, so I get 1 by 4. Remember that cos of 0 is 1. The next case I get f pi by 2 is 0. Remember, cos of pi by 2 is 0. Now the two more cases are there, f pi by 6, f pi by 3. We can again find these out very quickly. Remember that pi is going to be 180 degrees, so you can simply get 180 by 6 and 180 by 3, and you can calculate these if you know the value of cosine and sine. If you don't, you can do it in the calculator, which I did, and I got these values here, and then I got this expression for I. Now, one of the reasons I do these hand calculations is I'm going to use it as a check for the computer program. So I have this nice looking number here, 0.183365, which is the coefficient of 3. and we are going to print it out to see if we get this number. Now if you calculate this I, you get 0.1571, which is actually pretty close to the actual optimal point. Let us now write our Fortran program. So the first thing is we have to write the main program. So I define pi as arc cos -1, a is 0, b is pi by 2, n is 3. I know the exact solution. It's 1/3 3 log 2 minus log 5. That's what I have written here. Remember, a log is ln as far as Fortran is concerned. And then I'm going to write a function. I'm going to call it simp38, and it's going to take a and b and n, and as the output it's going to give me the value simp38. So that function is going to help me calculate the estimate of the integral which is coming out of the Simpson's 38 rule. And then I'm going to print this estimate of the integral, and I'm also going to print the exact solution so that I can compare these two values. Of course, I'm going to need a function which is going to calculate this mathematical function. So I simply write this very simple function here. So essentially f is cos x by 4 plus sin x into 1 plus sin x. Remember, all these functions are built into Fortran, so there is no need to call any library like NumPy or math in Fortran as you may have to do in Python. So let us write this function here. So I have written this function. Now this function essentially translates this formula into the computer program. Now I am going to define these two summations as two terms t1 and t2, and I'm going to set these to 0. H is b minus a by n. Remember, n is coming in, a and b are coming in. These are the bounds on the definite integral. Then I have the first do loop which calculates t1 and the second do loop which calculates t2. Now in the case of t1 there is a slight level of complexity because you have to skip all the multiples of 3. So I have this piece of code there that if mod k3 is not equal to 0, then you do this. So actually you can check out the mod function and you can see that this will go in such a manner that all the multiples of 3 are going to be skipped. And in the second case, of course, I simply have the bound going from k is 1 to n by 3 minus 1. Now remember, here I have not specified somewhere that n has to be a multiple of 3, but when you input, you have to consider that. Of course, if you are writing a more practical code for commercial purposes, you should have some built-in logic saying that n should be 3 if some user inputs a number which is not. So n has to be a multiple of 3. Then I finally write the formula for the Simpson's rule. So I get 3 by 8h. So that's here. Then you have fa plus fb plus 3 into term 1 and 2 into term 2. So this is hopefully going to give me the output. I put this entire program in onecompiler.com. That's an online resource which you can utilize for checking your Fortran programs. And you can see here I have copied and pasted the main program here, and this is essentially the function simp38. Now of course what I have here are I have the functions which give me the function f of x, and then I also have the Simpson function here. So I'm going to run this program and then I'm going to show you the output in the next slide. So this is the output here. You can see the term 1 is 0.1833. That's the number I also got from hand calculations. And also the second term is simply 0. So in this case, what happens, the second term does not actually get activated at all. So that is something which is particularly nice in this case, or I should say that's problematic in this case because we have not tested the logic of that term. And the integral comes out to be 0.1570, which is pretty close to the exact value, which is 0.1567. Now the case n is 3 actually does not test the second part of this summation. So what I'm going to do is I'm going to try n is 6. Now n is 6 is going to test two situations. It's going to test the second part of the summation. That's the one involving the coefficient of 2. And also I'm going to be able to check the logic I have here where k is actually a multiple of 3. So if I have n is 6, then I am going to pass through 3 here. So that's going to be checked also. So again, I write this expression like this. Remember, n is 6, so n minus 1 is going to be 5. and n by 3 minus 1 is going to be 3 minus 1, that is 1. So n by 3 is going to be 6 by 3, that is 2 minus 1, so that's going to be 1 here. So now I can expand this out and I'm going to get this expansion here. I'm going to get the term fx1, fx2, fx4, fx5. Remember, fx3 is not going to be present in this summation, and the second term is going to involve fx3 only. Now what I have done, I have taken this and then I have got each of these components. A we know to be 0, P we know to be pi by 2, but what takes place here is that I have all these remaining terms. So in fact, I have got these terms, for example, x1, x2, x3, x4, x5, and so on. And so I get the values corresponding to each of these terms. So you can get all these values once you realize that h is pi by 12. And these are all going to be some multiple of pi. And then I can express I in this form here. Now what I need to do is I need to calculate the function value at all these points, that is at 0, pi by 2, pi by 12, pi by 6, pi by 3, 5 pi by 12 and pi by 4. Now this is a pretty laborious process, but I have done it on the calculator and I have obtained all these results here. Now some of these cases are easy because remember pi is 180 degrees, so if you divide it by different numbers you will get various multiples of 15 in this case, and you will get all these values here. So we are going to take all these values and then we are going to substitute it in the expression for I here. So I have done that here, and after a lot of calculations I get this last expression here. So here you can see I have these two expressions in red. This is corresponding to term 1 and term 2, which I'm going to check from the computer program. And also I can finally get the expression as 0.1567 using this Simpson's rule. Let's put it in the program, which I have done here, and here I have put n is 6. So you can see the program is essentially same. The only difference is n is 6. Now once I have this program, I can run it, and after I run it I should get the output. Now one thing I have introduced here, I think I have not done it in the previous programs, is that if you have multiple declarations, for example in Fortran, you can separate them by semicolons here. The output comes out to be these values. Again, these values 0.39, 0.799, they match the calculation which I have done. So again, you can go there and check it out. So that's where you are going to get the solutions, and the solution is pretty good but not too good. Still you would have expected a better solution, but it doesn't come out so in this case yet. So what I do is that I have the program so I can take advantage of it. I put in a do loop. I go from 3 to 126 and I change it by 12 every time. Remember, I have to get n as multiples of 3. So this particular selection ensures that, and then I should converge to the actual results. So these are the solutions which I finally get. Of course, the exact solution stays the same, that is 0.1566678773, and I get the estimate Simpson's 3/8 rule matching that at n is 123. So pretty much discretization is required here, but not as much as in the trapezoidal rule. Now one of the things which may happen here is that the function here is probably closer to quadratic than cubic. So that's why I think Simpson 1/3 rule may have performed better in this problem. If you haven't checked my previous tutorial out, make sure go back and check it, because that's going to help you understand that particular method also. Now as a check, again we will turn to Wolfram, and here I have taken the function, plotted it, and actually calculated the definite integral value, which comes out to 0.15666, and you can see this function is more of a quadratic than a cubic. So maybe because of that the Simpson's 1/3 rule worked out best for this function. It converged with the lowest value of n. Now I should give you some homework problems so that you get some practice. So one of the things you can do is that write a double precision code and essentially implement the Simpson 3/8 rule. Also look at derivations of this rule out there in the literature. If you search Google, you will find many different resources. You can also look at any book on numerical computation if you are interested. And you can see that you have a choice of trapezoidal rule, Simpson rule, and Simpson's 3/8 rule. And in all these three rules, one of the things is that the mesh you are using is a uniform mesh. So essentially you are dividing that region A to B in small segments which are all having the same length given by h. And in those cases, you are getting the different programs out there, the different rules out there. Now, from the derivation, you know that trapezoidal rule would be good for functions which are almost linear. Simpson 1/8 would be good for functions which are quadratic types, and the 3/8 rule would be good for more nonlinear functions, maybe functions which are coming close to the cubic type of polynomial. So depending on your function, the rules are going to behave differently. So you cannot simply say that the 3/8 rule is going to be always better than the 1/8 rule and so on. It is again, like in many cases in numerical computation, a case dependent situation. So before I end, I'll just leave you with the 3/8 rule. It's called 3/8 rule because you have 3 by 8 into h. The first two terms are fa plus fb. Then you have this term which is a summation of various values k is 1 to n minus 1, but excludes multiples of 3. So this particular sign here means that it excludes the multiples of 3 here. And then we have a second summation here going from k is 1 to n by 3 minus 1. And of course, you need to consider k to be a multiple of 3 because you are, for example, dividing by n by 3 here, and you want this to be a number which is being divided properly. So that's something to keep in mind. So this was my take on the Simpson 3/8 rule. I think now you have a bunch of rules which I have given you, which you can use for numerical integration problems. Numerical integration comes up in many places, and these rules are also useful in situation where you actually have data. So you may not have function, you may just have the function values and data at a uniform grid, and then you can use these rules to calculate the value of I there. Now there are some rules which are more useful for functions where you do not need to take a uniform grid. These are to do with the Gaussian method. So I think I'm going to discuss the Gauss-Legendre quadrature next, because that is widely used in problems where you actually know the functions, typically polynomials. For example, in FEM type situations. So there very often we use polynomials, and then Gauss quadrature works out very well. So I'll see you in a video sometime soon on that method, but do subscribe to my channel and stay tuned to the channel because that's certainly going to help you.